In this video, we'll go over a couple of examples using the squeeze theorem. The idea behind it is, let's say you have a couple of functions, f of x and h of x. And you know there's some other function, but you don't have a formula for it, but we'll say that this other function, g of x, is between both f and h. If you look at the limit, as x approaches 1 of f of x, well, that limit's going to be 2 because the formula is 2x. If you look at the limit as x approaches 1 of h of x, if we put 1 into that, we get 2 as well. Using this information, can we figure out what the limit as x approaches 1 of g of x is equal to? Even without having a formula for it, can we actually figure out this answer? And by the squeeze theorem, we can actually say it is equal to 2. The reason is, if you know what the outside functions are doing, and you know their limits, since this function g is between these two, it's forced that the limit is also equal to 2. Let's look at a graphical reason as to why this works. Here I have graphs of f and h from the previous slide. So the one that is in red, the linear one, is f of x, and the one that is in blue is h of x. Now, from the graphs of these functions, we can figure out both the limit as x approaches 1 of f of x, and also the limit as x approaches 1 of h of x. So that is, here at 1, the limit of f is 2, and the same thing is true for the function h. So this has a limit of 2, and this has a limit of 2. So you can either use the formulas, or we can actually use the graph here as well. What does it mean if we introduce a third function, g of x, that's between these two? That is, f of x is less than or equal to g of x is less than or equal to h of x. We don't have a formula for it, but if you want to draw that in here, it's got to do something like this. Your function has to be lower than the blue graph, but above the red graph. So you get something like this. I'll start it here. So here's a function g of x. I don't know what it is, but it's certainly between the two functions f and h. And as we get closer and closer to 1, if this still remains true, this has to squeeze in here and actually go to the value of 2 at x is equal to 1. And then it'll pass through on the other side. This is why, if the lower function has a limit of 2 at 1, and the upper function also has a limit of 2 at 1, it must be true that the limit of g goes to 2 as well. That is, the limit as x approaches 1 of g of x is 2. So you can use the squeeze theorem to justify this without even knowing what the formula of it is. One final thought is this fact that f is less than g is less than h only has to be true if you're actually near the value that you're taking the limit of. So just to draw this in here, it could be that your function g, maybe it goes above one of the functions or below one of the functions, but as long as you're near this value, then this fact remains true. Let's look at one more example where we use the squeeze theorem to evaluate a limit. So if you try to figure out this limit, you unfortunately can't just put 0 in place of x because you would divide by 0, and that's not defined. The way you can use the squeeze theorem here is to use the following fact. Cosine of any angle, whatever you put in place of it, it's always less than or equal to 1, and it's always greater than or equal to negative 1. I'll note that this is also true for sine, so sine of any angle has the same property. But for this problem, we're going to use this one here. And here's how this will work. So we'll start with cosine of 2 over x. By this fact, no matter what you put here where this is defined, this expression must be less than or equal to 1 or greater than or equal to negative 1. So that is, this is always true as long as x is not equal to 0. What you can do next is multiply through this inequality by x to the 4th. So here on the left, I'll multiply by x to the 4th, and I get negative x to the 4th. That's less than or equal to x to the 4th times cosine of 2 over x, and that's less than or equal to x to the 4th. Because x to the 4th is positive, it will not change the direction of the inequalities when you multiply through by it. Now, how does this help us solve the limit up here by using the squeeze theorem? Well, this is the thing that we want to figure out the limit of, and we're approaching 0, and we have a function that's above it, and we have a function that's below it. Let's look at this lower function. What happens if you take the limit as x approaches 0 of negative x to the fourth? Well, we can figure this one out by just simply putting 0 in place of x and get an answer of 0. So this thing here goes to 0. Great. Now, what about this piece over here? What is the limit as x goes to 0 of x to the fourth? Well, that's 0 too. So this thing also goes to 0. By the squeeze theorem, we can now say, since this function is less than this function is less than this function, and these two limits are equal, we can apply these pieces together and say, by the squeeze theorem, the limit as x approaches 0 of x to the fourth times cosine of 2 over x is equal to 0 as well. And here, because we're talking about a limit approaching 0, we don't have to worry about what happens at exactly 0, but we do know that this limit does exist.